IP Tech Talk. Hello everyone, welcome to IP Tech Talk. In this video, I'll be talking about the differences between telemetry and SNMP as the nervous system of intelligent network O&M. As we all know, the rapid development of Wi-Fi and the Internet of Things has led to a proliferation of device nodes and access terminals on campus networks. Research shows that about 10 billion terminals were connected to networks in 2010, with that number expected to rise to 50 billion by the end of 2020. This makes network O&M more difficult than ever and puts much pressure on network engineers. So, how can we free network engineers from heavy workload? Actually, many industry-leading vendors have proposed the idea of intelligent network O&M, such as HUAWEI's Intelligent Campus Network O&M system, which is a basic architecture that looks like this. Campus Insight can be thought of as the brain of the entire intelligent O&M system, while network elements and terminals are like the torso and limbs. The collected network service data is sent back to the brain of the intelligent O&M system in compliance with a certain protocol. That protocol can be considered as the nervous system. SNMP is the protocol traditionally used for this purpose. But due to numerous shortcomings of SNMP, it is gradually being replaced with telemetry. In this video, we'll look at these shortcomings of SNMP and how telemetry helps to overcome them. Now, let's look at the issues with SNMP and why it cannot meet the requirements of intelligent O&M. First, SNMP-based network monitoring is not accurate. SNMP needs the NMS to periodically send query messages, also known as GET messages, to read performance indicator data of network devices. However, the SNMP queries are usually sent every 5 minutes. This may lead to the following situation. A customer reports poor network quality, such as the video freezing or pixelation problem. However, after checking the network on the NMS, a network engineer finds that the network is normal. Why is that? Surely the customer isn't making this up. Does the problem lie with the network engineer? Who should be responsible? Actually, both the customer and network engineer are in the right. The network quality does indeed deteriorate, and the NMS does not detect it. So why is this happening? Let's take a look at this graph. Assume that it is showing the interface traffic on a switch. The network is normal upon the first SNMP query on the NMS. After 5 minutes, another SNMP query is initiated, and the network is still normal. Everything seems fine, right? However, during these 5 minutes, the network has actually experienced quality fluctuations and even traffic bursts. The issue is, SNMP does not detect the problem. This is why we consider the data collected by SNMP to be inaccurate. The root cause is that the data collection interval is too long. Some people may think that this problem is easy to resolve by shortening the SNMP data collection interval. While this method does work to some extent, it also brings another problem, which is high CPU usage. If you were a network engineer, you must have handled many issues related to high CPU usage. I'm sure you often find, after looking everywhere for the root cause, that actually it is caused by the SNMP process. Why is that? This is actually related to how SNMP works. SNMP collects data through a series of requests and responses as the NMS periodically queries data from devices. For example, the NMS asks a switch, "Hey switch, what is your CPU usage?" The switch then passes the message received from the NMS and sends its CPU usage to the NMS. However, that's not the end of the story. The NMS keeps asking the same question, so the switch needs to continuously pass the messages sent by the NMS. At the same time, the switch needs to keep forwarding data packets. That's a busy switch, right? On a live network, the NMS queries many device indicators, such as the interface rate, memory, and optical power. Over time, this causes excessive CPU usage on the switch. This kind of SNMP data collection mode is also known as the pull mode. That means that a question is asked and a response is returned. Of course, SNMP also supports the push mode through trap reporting. However, the push data is usually alarms and events. SNMP does not support the push mode for a larger number of network performance indicators. In addition to the two major problems I just introduced, SNMP has other problems. For example, SNMP messages are transmitted via UDP, which is an unreliable protocol. If data is lost, it's lost, without even a notification being sent. As another example, the SNMP data structure depends on MIB objects, each having an identifier such as 136XX, and these objects are difficult to memorize and use. Today, I'm not going to list all of SNMP's problems one by one, and if SNMP could talk, I'm sure it would say, "You say that I have many problems, but don't you realize my name means Simple Network Management Protocol? I was created to be simple. If you need me to support big data intelligent O&M, I'm afraid that's definitely beyond my capabilities." Okay, so let's not keep criticizing SNMP. Instead, let's see how telemetry resolves these problems. Let's start with data collection precision. First, the telemetry collection interval is at the second or even sub-second level. Second, telemetry allows one subscription packet to carry multiple pieces of sample data, reducing the number of exchanges between the NMS and devices. Third, data collected by telemetry carries a time stamp. When passing data, the NMS determines when the data was sampled based on the timestamps. This prevents the impact of network transmission delay on sampled data. By leveraging these approaches, telemetry improves the precision and accuracy of data collection. Now, let's look at the data collection mode used by telemetry, the push mode. With telemetry, network devices can proactively report various types of data to the NMS if they have subscription configured in advance. They only need to pass the first query message, after which they report data proactively. In this way, CPU resources on the network devices are no longer passively scheduled, as is the case with SNMP. Instead, network devices can proactively and effectively schedule their CPU resources. This overcomes the high CPU usage problem caused by SNMP. Lastly, telemetry integrates raw data collection, data modeling, encoding format, and transport protocol. It organizes the collected raw data based on the data structure described in Young models, encodes data using GPB, and sends the GPB encoded data to Campus Insight through the Google Remote Procedure Call, or gRPC protocol, over an encrypted channel. In conclusion, telemetry-based data collection provides Campus Insight with accurate, real-time, and rich data sources, building a basis for intelligent O&M. Telemetry enables both wired and wireless devices on the entire campus network to collect data effectively, implementing intelligent and automatic network O&M. Well, that brings us to the end of today's IP Tech Talk about SNMP and telemetry. Thanks for watching, and see you next time.